Hello, this is the second video of a fourth Graphics and Networks series on route inspection and the travelling salesperson problem for OCR Discrete Further Mathematics. And we will consider the larger problems for route inspection, where networks are neither Eulerian nor semi-Eulerian. In the previous video, we looked at the idea of a network being traversable or Eulerian, with all even order nodes, or semi-Eulerian with one pair of odd nodes, and the solutions for the route inspection problem for these types of networks. In this example, there are two odd pairs of nodes. We start by identifying the order of each vertex. A is of order 3, B is 3, C is 3. D is 4, E is 4, F 4, G 4, H 2, I 3, and J 2. So the odd nodes are A, B, C, and I. We know we'll need to pair the odd nodes in order to find a way of joining them. So let's consider which pairings will lead to the minimum weight of arcs to be added. The options are that we could pair A and B, in which case C and I would be paired, or we could pair A and C, giving the other pair as BI, or we could pair A with I, then with B and C paired. Well, we can see that A to B, the shortest, most direct route, is 100. However, for C to I, there are various options. We could go via B and E and G, which would give us 120, 250, 100 and 100. Or we could go via F and J, giving us 200, 160 and 80. The shortest of these routes is to go via F and J, giving 440. And thus the extra weight of joining A and B together and then C and I together would be 540. Looking at the next option, A to C would either be via B 100 plus 120, or the direct route up the top just of 150. I will write down 150. For B to I, the shortest route is straight down via E, G, 250 plus 100 plus 100 at 450, thus giving potential added weight of 600. Thinking about AI, we again need to look at different options. We could go via D and H, so 200, 160 and 40. Or I could go A, D and then to G and I. This looks like the shortest route at 380. And then BC, you can see the direct route is 120, giving 500. We can see that this adds the minimum weight to have these pairings of odd nodes. You can also see here that my total is 2090 for all the existing arcs being added together. So, thus, for these two odd pairs, the best or the minimum total weight that I can come up with is the 2090 plus that 500, giving me 2590. So in summary, first of all I needed to identify the odd nodes, realizing that they will always come in pairs. I then need to look at the possible pairings and look at the different routes. So, for example, between A and I could have taken this route or this route, or I could also have considered this route to see which is the least weight. Once I've identified all the least weights for the possible pairings, I then compare them and check to see which was the minimum. I then needed to add this to the total. Here is that summary on a slide for you to read through. Remember, it's very important that if you need to identify a route, then make sure you repeat the edges used in step 3 when you list it. So, identifying a pathway around that network which would now be traversable with those extra edges between those odd nodes, make sure you include those. Note that this algorithm can be applied to networks with any number of odd nodes, and that also in step 2 we could use Dijkstra's algorithm, but generally we do it by inspection. So for more than 2 odd pairs the algorithm will still work, and in questions you may be asked to apply this for networks with up to 6 odd nodes. Just be careful to list all the possible pairings. Let's consider these. So the number of pairings you increase the number of odd nodes. Well, for one pair there'll just be one pairing, and you'll just be trying to connect, say, A and B. For 2 pairs, let's say you've got the option of connecting A with B and then C with D. However, you could of course also connect A and C and then B and D, or A and D and then B with C. So you have an initial choice for your first pairing where you have 3 choices, and then once you've done that you don't have any more choices, so it's just 3. You could write that as 3 times 1, and then you get resulting in 3 different distinct pairings. If you have 3 pairs or 6, and let's use the letters A through to F for this, again let's start by considering A paired with B, and then you have 3 options similar to the ones here, in terms of you can have CD plus EF, or you could have CE plus DF, or CF plus DE, each of those with the AB. You would then look at AC and so on down to AF, each of which would have those 3 options. So therefore we're looking at 5 choices for A to initially pair with, and then thereafter for each of those you've got this 3 times 1 worth of choices, and thus 15 pairings when you have 6 odd nodes or 3 pairs. From this we can generalize that the number of pairings as you increase the number of odd nodes is, for 2n pairs, that product 1 times 3 times 5 up to 2n minus 1. In the next video we introduce Hamiltonian cycles and the travelling salesperson problem.